Okay, in this short video, we'll talk more about reflections and translations. And start off with this. Since any product of reflections has the ABCD property, we talked about that in an earlier video. Remember what ABCD stands for? I'll write it here. Angle measure, that's the first one. The B is betweenness. The C is collinearity. And the last one is distance. And we already learned that reflections and products of reflections maintain the angle measure of your set, maintain betweenness, maintain collinearity, and distance, A, B, C, and D. Because of that, translations and rotations will also maintain all four of those. But translations and rotations preserve orientation as well. So if they preserve the orientation, they are direct, not opposite. Now, reflections, remember, that's not listed here. Reflections reverse the orientation, so they would be considered opposite. Okay. Move on to number 6. Every single translation can be written like this. F, what does F do to xy? We could have written it as F of xy equals. We left off the xy though, which is common. How do you get the new x prime, y prime? You simply add or subtract a number. We'll say x plus a. Now a could be negative. And then y plus b. And again, b could be negative. A and b can be any real numbers you want. If a and b were both 0, this would simply be the identity transformation. X prime would be x, y prime would be y. It would do nothing. Okay, number 7. If you, in a translation, it can be completely determined by one point. One point, I'll call it Z, and its image, Z prime. If you know what this translation does to one point, you know what it does to all points. It does the same thing to all of the points. It might, for example, move one point to the right 2 and up 3. It'll do that then for every single point. So let's look at an example here. A translation that maps point A to B is written like this. Little t for translation. And then A and B are 2 points. And so let's just say that A is the point 1, negative 2. And point B is negative 1, 5. Find TAB of xy. Then let's find TAB of a very specific one, 7, 3. This is finding everything. This tells us what to do. Okay, so let's see what TAB is. T lowercase or subscript AB of xy. Well, I could write it like this. X prime equals y prime equals. I could have written it like an ordered pair, but I'll write it this way. All you need to do is say, what did we do to this x value A to get to this x value B by adding or subtracting a number? 1 to negative 1 means we subtracted 2, right? 1 minus 2 gives you negative 1, so it's going to be x minus 2. Now, y prime, what did we do to negative 2 to get to 5? We added 7. That's how you'll compute the image for every single point under this translation. Okay, so now specifically it says, find TAB of 7, 3. Well, that's going to be really easy. It's just an ordered pair. What do we do to find x prime? We do x minus 2. 7 minus 2, 5. For y prime, we do y plus 7. So negative 3 plus 7 to get the y prime would give us a 4. And that's it. Okay, now let's move over to a rotation. Rotation you can think of as working with a circle that has a center, and you're rotating it around the circle. So a rotation is completely determined by its center. We sometimes call that capital C. And its angle of rotation. How far do you want to rotate it? What angle of rotation? Well, a rotation with center C and angle of rotation theta can be denoted like this. That's how we would write it. R for rotation, theta is it could be 90 degrees, 72 degrees, something like that. And C will be an ordered pair that would represent the center of the circle that you're rotating around. Okay, let's do a real easy one. Given given the center is 0, 1, and there's a point Q, negative 3, 1, and our angle of rotation theta is 180 degrees, find this. So this says the rotation of 180 degrees around the point 0, 1, starting with the point Q, negative 3, 1. Well, this will be really easy if we just draw a picture. Let's go out 1, 2, 3, and maybe negative 1, negative 2, negative 3. And I think we only need to go up 1 for our graph. So the center is 0, 1. That's our center. That's what we're rotating around. The point we're rotating is Q. So let's go to negative 3, 1. That's our point Q. What am I going to get if I rotate around a circle, around the center C, like this, but I'm rotating 180 degrees? It's going to take me half a circle. So this one, you don't need to have a protractor, compass, anything like that. You know that it's just going to you're going to end up right here. That would be, maybe I'll call that, I could call it Q prime, but I'll call it R theta C of Q. All right, that's that point right there. So that one was very simple because it was rotating at 180 degrees. If we would have rotated it only 90 degrees, we would have ended up about here. Or if we rotated it 180, say 270, we would have rotated it all the way around to there. Okay, let's move on to number 9. This is a lemma, very simple lemma, called the identity isometry. If an isometry fixes a certain number of points. Remember what fixes means? It means it does not change them. Like, if a function f of 5 equals 5, it means it doesn't change that value. It means it's fixed, the number 5 is. If an isometry fixes 2 points of a line, then it fixes the entire line. Okay, so that means every point on the line going through those 2 points would also be fixed. So that the transformation or the isometry doesn't affect that line. It does nothing to that line at all. The identity map, we sometimes call it E. It maps a point P to P. Like with real numbers, the identity function is f of x equals x. It doesn't change the value. So the identity map that maps a point to itself is given by, of course, this for every point x, is the only isometry that fixes 3 non-collinear points. So if you have 3 points in the plane, And the isometry, if f of A is A, f of B is B, and f of C is C, it does nothing with those 3 points. That means it does nothing with any of the points. In other words, it's the identity mapping. 10. If you take two isometries, functions for which distance or length is preserved, take two isometries such that they're f and g. F of the triangle ABC gives you triangle XYZ, but also G of the triangle ABC gives you triangle XYZ. So they map one triangle to the same triangle. That means they map every point the same. So in other words, those two isometries are identical. If they map 3 points the same, they map all points the same. I guess I should have said 3 non-collinear points, making a triangle, of course. All right, last one in this video. Theorem, isometry triangle congruence. All right, if you take two triangles that happen to be congruent, okay, so that means they have exactly the same angles, the same side lengths. They don't have to be in the same place, but just think of them as the 3 side lengths being the same. Then there is exactly a unique isometry F that will map F of triangle ABC to triangle DEF. There's exactly one isometry that will map that triangle to this triangle.